Hello, I'm going to report this paper, Orientation Condition Visual Texture Mapping for Video-Based Visual Remote Photoplethysmography Estimation. And this is my outline. I will present this paper by four parts. The first is introduction. In medicine, ECG and PPG are important tools for obtaining information about the heart, using contact methods to capture signals. In recent years, non-contact methods for signal acquisition have been developed, known as RPPG. Nowadays, many conventional methods have been proposed, such as Chrome, PSS, ICA, PCA, CREAN, and so on. However, conventional methods for obtaining RPPG signals are limited, and there is a growing demand for more diverse cardiac features in RPPG applications. Therefore, deep learning approaches for extracting RPPG signals have emerged. These methods are data-driven and possess strong fitting capabilities, making them one of the mainstream directions. This paper introduces a novel methodology using deep learning that leverages the three-dimensional visual surface to construct an orientation condition visual texture video representation, improving the motion robustness of existing video-based visual RPPG estimation methods. The process begins with standard video input, which captures the subject's visual appearance. This video, this raw video data contain both the subtle color changes relevant to RPPG analysis and unwanted variation caused by subject movements. The core of this system is a video pipeline, which processes these input frames through several key stages. The first stage performs orientation condition visual texture mapping, transforming the regular video frames into a specialized representation that accounts for the three-dimensional orientation of the face. This transformation helps maintain signal clarity even when the subject moves. After the video processing, the transformed frames are fed into a video-based model, specifically a business 3D CNN architecture. This deep learning model has been trained to recognize an extra subtle patterns associated with blood flow changes in the face. The final stage of the pipeline produces two key outputs. First, the RPPG signal representing temporal changes in blood volume observable through the skin. Second, the pulse rate is emitted from the signal. This output provides variable physiological information about the subject, all captured non-invasively through video. The input consists of standard video frames captured by a camera. First, the system establishes a camera normal vector, defining the camera's viewing direction. The system then performs three-dimensional landmark detection on this frame, creating reference points across the face. In the first processing track, the system processes visual appearance. It combines the three-dimensional landmark detection result to generate XY appearance frames and corresponding three-dimensional meshes. Through a specialized transformation process, these are converted into UV appearance frames into UV coordinate space, effectively mapping the three-dimensional visual structure onto a two-dimensional texture space. The second track focuses on orientation processing. Here, the system calculates the orientation angle theta sub v for each vertex and transfer this information into UV coordinate space, creating UV angle frames theta UV. This calculation generates UV appearance mask that identify regions where distortion might occur. The final step combines the UV appearance frames with the UV appearance mask to produce orientation condition visual texture frames, preserving essential visual features while eliminating areas prone to distortion. In the top row, four image illustrates how visual regions are highlighted in green based on different angle threshold relative to the camera. This progressive visualization aids in understanding how different visual orientations are processed in the system. The bottom row reveals the three critical stages of the UV texture mapping process. On the left, the UV angle frames is visualized in a blue-purple gradient, representing the computed angle between each point on the visual surface and the camera. The middle image shows the UV appearance mask in yellow, created using optimal threshold of theta UV less than 45 degrees. The final image on the right demonstrates the result after applying this mask to the visual texture. The VCNet 3D CNN architecture is designed to effectively extract RPPG signals from video sequences from its specialized deep learning structure. At its core, the network uses three-dimensional convolutional layers to simultaneously process both spatial and temporal information from the input video frames. The network begins with preprocessed video frames and progressively learn more complex features from multiple convolutional layers, each followed by batch normalization and ReLU activation. The spatial dimensions are gradually reduced while preserving crucial temporal information. The network concludes with transposed convolution to construct the temporal RPPG signal as the original sampling rates, enabling accurate post-rate estimation. Table 1 presents the comparative results of different RPPG estimation methods tested on the pure dataset. The methods are categorized into three groups: signal processing methods, video-based deep learning method, and estimate-based deep learning method. The analysis shows that traditional signal processing methods like Chrome and Pulse achieve mean absolute error value ranging from 2.07 to 5.77 bits per minute. Deep learning approaches demonstrate improved performance with ETL RPPG nets, achieving a particularly impressive NAE of 0.34 bpm. A proposed method VCNet XY and VCNet UV show strong performance, excluding subject 7 token. The NAE value are 0.341 and 0.5 bpm, respectively. Including all subjects, the NAE increases to 1.318 and 1.639 bpm, while VCNet UV shows slightly higher NAE in this intra-dataset testing. Its true advantages become apparent in cross-dataset scenarios. The proposed VCNet UV demonstrates superior performance with an NAE of 12.187 ppm, showing an 18.2% improvement over VCNet XY's 14.905 ppm. The correlation coefficient also improves significantly by 89.8% from 0.155 to 0.294. These improvements surpass traditional signal processing methods like clone and pose, as well as other deep learning approaches such as deep physics and physiformer. These results strongly validate the orientation condition approach's ability to handle data from different recording conditions. Table 3 demonstrates the performance comparison between VCNet XY and VCNet UV across various motion conditions. The result validates the orientation condition approach effectiveness in handling different types of subject movement. The most significant improvements appear in rotation scenarios, where VCNet UV achieved a 29.6% reduction in NAE. Stationary scenarios showed a 21.5% improvement, and walking scenarios demonstrate a 20.8% reduction in NAE, while talking scenarios shows more modest gain with a 7.5% improvement. The overall result confirms the method's robustness across different motion types, particularly in handling changing head rotation and movement. Tab 4 shows the impact of different processing components in the pipeline flow ablation studies. The baseline VCNet XY with static cropping achieved an NAE of 14.905 ppm. Introducing UV transformation with various orientation angle threshold demonstrates that a 45-degree threshold provides optimal performance, achieving an NAE of 12.187 ppm. Importantly, the order of processing steps matters. Applying UV transformation before frame difference yields better results than the reverse order, while dynamic cropping generally shows lower performance. Adding segmentation helps mitigates some motion-related issues. This finding confirms the importance of the orientation condition approach in the processing pipeline. And finally is a conclusion. The UV coordinates texture mapping technique has proven superior to both dynamic and static phase detection methods. These improvements stem from the ability to better handle visual movement and variation while maintaining signal quality. Particularly impressive performance improvements were observed across various motion scenarios as evidenced by cross-dataset testing results. However, limitation of the current approach remain during the UV coordinate texture mapping process. Geometric distortion may occur, potentially impacting training performance. This challenge highlights an area for future improvement in the methodology. Future research opportunities include integrating the proposed representation with more sophisticated video-based frameworks, Combining the orientation condition approach with state-of-the-art deep learning architectures could achieve even better results in challenging real-world scenarios. Thanks for listening.